Number 6, numerical number 6.3. Long solenoid with 15 turns per centimeter has a small loop of area 2 centimeter square placed inside the solenoid normal to the axis. If the current carried by the solenoid changes steadily from 2 ampere to 4 ampere in 0.1 second, what is the induced EMF in the loop? Now see, we want to find out the induced EMF. Now what is the situation here? First of all, try to understand the situation. There is a solenoid. Okay, in the solenoid there is one loop which is placed. Its area vector is in in the direction of axis of the solenoid. So angle between magnetic field of solenoid and area vector, okay, the angle between magnetic field of solenoid, that is in this direction, and area vector, they are parallel, so the angle between them is 0. So now if you want to find the flux, then it is BA cos 0. Now magnetic field of solenoid, we know it is mu 0 Ni into A. Now according to Faraday's law, E is equal to minus d phi by dt. So induced EMF will be equal to minus mu 0 N A. It becomes di by dt. Why di by dt? Because current changes here. Mu 0, number of turns per unit length, area vector, the value of area of this small loop, that remains constant. Okay, so now this n, if you find, n is given indirectly 15 turns per centimeter. So 15 upon 0.01. Okay, this will be the small n. Then area is given 2 centimeter square, 2 into 10 to the power minus 4 meter square. Okay, 2 centimeter square. Then di by dt you can easily find. Current changes from 2 to 4. So final current is 4. Initial is 2. In how much time? It is in 0.1 second. So this value you can find. Mu 0 is known to you. If you put these values here in this equation, then you will get the final answer, that will be having negative sign. A negative sign shows the presence of Lenz's law, and if you find the magnitude, then make it positive. Okay. Now 6.4, a rectangular wire loop of side 8 cm and 2 cm with a small cut is moving out of a region of uniform magnetic field of magnitude 0.3 Tesla directed normal to the loop. What is the EMF developed across the cut if the velocity of the loop is 1 cm per second in the direction normal to the longer side and then shorter side? Okay, for how long does the voltage lasts? Okay, now for this, first of all, we consider a rectangular loop. Okay, this is the rectangular loop which we are considering. Okay, there is small cut here. Okay, here it is complete cut is here, and the magnetic field is, say, going inside the plane. Okay, now see, when this longer side goes out first, then the flux associated with this rectangular part changes, and according to our formula, E is equal to BVL, as if this longer side is moving in the magnetic field. Okay, so the value will be, magnetic field is given, it is 0.3 Tesla. Velocity of this longer side is also given, it is 1 centimeter per second, so 1 into 10 raised to minus 2, and length of this longer side is 8 centimeters, so 8 into 10 to the power minus 2. So if you simplify this, then you will get 0.24 millivolt. Okay, if longer side is moving in this particular direction. Now if you move this way, then shorter side is moving, then this part goes out of the magnetic field first, and then this again magnetic field is changing, but here instead of length we have to take now breadth, this part. Okay, so try to understand it this way. Say you have this rectangular same loop, cut is made here, and you take this way. Okay, then this breadth is moving in this magnetic field and the flux changes this way. Okay, so the electromotive force is BV. Now instead of length you take breadth and put the value of breadth. This velocity magnetic field is already same. Breadth is 2 centimeters. So instead of B we have to write 2 into 10 raised to minus 2. Okay, instead of this B, and you will get the answer of electromotive force, that is 0.06 millivolt about you will get. Okay, now time for which the magnetic this electromotive force persists, that we want to find. Now when this part is moving along the length side, then to remove this from the magnetic field, it has to travel the distance which is equal to its breadth. To totally remove this out of the magnetic field, okay, then the distance which has to be covered is how much? It is equal to its breadth. So when length is moving out first, try to understand, when the length is moving out first from the magnetic field, then it has to travel the distance equal to its breadth. So the time for which this particular electromotive force persists, that time, say t1, is equal to, as you know, as speed is equal to distance upon time. So time is distance, that is first of all breadth upon its speed. Now breadth is known to us, 2 into 10 raised to minus 2 meter, and the speed is 1 centimeter per second. So it lasts for 2 seconds. The electromotive force lasts for 2 seconds. Now if you remove this way, then instead of breadth we have to write length, and the answer you will get, that is 8 seconds. Okay, now 6.6, a circular coil, or rather it is a 6.5. okay, 1 meter long metallic rod is rotated with the angular frequency of 400 radian per second about axis normal to the rod passing through its one end. The other end of the rod is in contact with the circular metallic ring. A constant and uniform magnetic field of 0.5 Tesla parallel to the axis exists everywhere. Okay, then calculate the EMF developed between the center and the ring. Okay, center and the ring we want to calculate. Now see, the circular ring is moving as such, this way. Okay, this is the circular ring and magnetic field is in this direction. Okay, this is the situation. We want to find out the electromotive force between the center and the circumference. Now see, say for example, the value of this electromotive force is given by the formula 1 by 2 b omega r square, where r is the radius or a length of this rod, whatever. Now very easy, 1 by 2, the value of magnetic field is 0.5. okay, and omega is given, it is 400 radian per second. So 400, the square of radius, that is of 1 meter, the square of 1, will get the answer, and that will be 100 volt. Okay, now 6.6. okay, Circular coil of radius 8 cm and 20 turns is rotated about its vertical diameter with the angular speed of 50 radian per second in a uniform horizontal magnetic field of magnitude 3 into 10 raised to minus 2 Tesla. Obtain the maximum and average EMF induced in the coil. Okay, if the coil forms a closed loop of resistance 10 ohm, calculate the maximum value of current in the coil, calculate average power loss. Okay, this we have to calculate. Okay, now see, this can be done easily. First of all, this coil is moving, and as you know, maximum induced electromotive force is given by E0, and that is equal to NAB omega. Place this value here. Area is pi r square, so N into pi r square P into omega. We just have to write the value here. Number of turns are 20. Pi 3.14 into square of radius, that is 0.08. Okay, because it is 8 centimeter, so meter ma 0.08. Magnetic field is 3 into 10 raised to minus 2 Tesla, and omega is 50. And if you simplify this, then you will get the answer to be 0.6029 volt. Okay, now average EMF, as you know, average EMF is nothing but E0 sin omega t. And if you want to find the average EMF, then you have to take the average of sine function over entire cycle, and average of sine function is 0, so average EMF is 0. Okay, then maximum induced current we want to calculate. Okay, maximum induced current I0 is nothing but maximum induced voltage divided by resistance according to Ohm's law. So you will get 0.6029 divided by the resistance, that is the 10. So 0.06029 ampere current it will be flowing. Then instantaneous power you want to find, then it is E square upon R. So the value E is nothing but E0 sin omega t. So E0 square sin square omega t divided by R. So this much you have to write first of all. Okay, P is equal to E square upon R, and E is nothing but E0 sin omega t, square of it, so it becomes E0 square sin square omega t upon R. Now try to understand power. E0 square upon R sin square omega t. I have just written in a different way. Barabar? Now average, if you want to find average power, then you have to take the average of this sine square, and average of sine square theta is 1 by 2. Average of sine square omega t over entire period is 1 by 2. So average power can be written as E0 square. As you know, E0 square we have 0.6029. 0.6029 average of this E0 square, then resistance is 10 ohm, multiply by the average of this sine square omega t, that is 1 by 2. And if you simplify this, okay, then you will get about 0.018 watt. 0.018 watt. Okay, now this power is lost in the form of heat, which is called the joule heat. Okay, now numerical number 6.7. Horizontal straight wire 1 meter long extending from east to west is falling with a speed of 5 meter per second at right angle to the horizontal component of the Earth's magnetic field. Try to understand right angle with the horizontal component of the Earth's magnetic field, whose value is 0.3 into 10 raised to minus 4 Weber per meter square or Tesla. What is the instantaneous value of EMF induced in the wire? direction of EMF and which end of wire that higher electric potential. Okay, now see, we try to understand this way. First of all, this is the wire. Okay, this is east direction and this is your west direction, and here this is north and this is south, and the angle is 90 degree that is given to us. Okay, now it is falling in this particular direction, the wire is falling in this direction. Okay, and horizontal component of the Earth's magnetic field is in this particular direction. So the angle is, rather we can say velocity is perpendicular to the magnetic field. Okay, the velocity of this which is falling down is perpendicular to the magnetic field. We can show it in a different color also. Say this is the direction of magnetic field. Okay, then this red color is the direction of velocity, so both are perpendicular to each other. And here induced EMF E is equal to BVL. Now see, horizontal component of the Earth's magnetic field B is given 0.3 into 10 to the power minus 4. Then velocity is given 5 meter per second. It is 5 meter per second, so 5, whatever. And length of this wire is given, it is 10 meter. So if you simplify this, so you will get the value of electromotive force. The question is, what is the direction of EMF? Now force acting on the charged particle at magnetic force is given by E V cross B. Try to understand, V cross B. Now velocity is in this direction, okay, and magnetic field is in this direction. So now if you use the right hand screw rule and rotate velocity in the direction of magnetic field, then the direction of force according to right hand screw rule will be in this direction, towards east direction, if the positive charge is there. Now the charges which are experiencing the force are negative electrons, so they will experience the force in opposite direction. So electrons will be accumulated in this direction or at this end towards west, and positive charge is opened up. So this terminal towards east will become positive, and towards west the terminal will become negative. Okay, so we can say that free electrons in the rod will displace in the direction towards west. Okay, so electrons will be displaced here towards west, and positive charge is opened up. So this terminal behaves as a positive terminal and this terminal behaves as a negative terminal. Okay,